So in this video, I'm going to go ahead and look at what happens when we take friction from being on a flat surface to being on an inclined plane. So if we look at friction just on a flat surface, we have a box of some sort. We would have our normal force pointing up, our gravitational force pointing down. If I were to push at some direction to the side or pull with something, I would have some sort of applied force, and then that would result in a frictional force back in this direction. Now, if it was moving at a constant velocity or if it was standing still, these would be equal, and then we know those two are equal. So what happens if I take this box, and instead of applying a force, I just incline the plane a little bit. So let's just draw plane that's inclined at some angle. Now, when I do this, if I just put my box on this table or on the plane, you can see that just by looking at it, this thing would probably want to slide down the hill, right? And that's because of gravity. Gravity makes it want to slide down the hill. But it's not the same as gravity straight down, because if there's some friction there, then the friction is going to slow it down a little bit, right? So there's actually some component of gravity that's pushing the object into the plane, and some of it that's making it want to come down the plane. Right? So let's just identify our forces here, and then we'll go ahead and look at what this means in terms of our sum of all forces equations. So I have a normal force, and normal force always points perpendicular to the plane. So this is going to be up off of the surface, right? And I'm going to put it in red. And I always have gravity, which goes down towards the center of the Earth. So it's going to go down, straight down in this direction. FG. And then, because gravity is wanting to pull it down the hill, but it's not moving, or maybe it's going at constant speed, there's got to be some frictional force moving upwards in this direction, which I'm going to put in blue. Right? Now, assuming that there is no excess like applied force, right? Gravity would be the only force making it want to slide down the hill. So a common error that kids want to put is they want to add in some sort of like applied force. But really the only force that's making it want to go down the hill is some part of gravity, right? So if we set this up as our coordinate system and we kind of look at it on its side, there are two different directions. There's the horizontal direction, which would be down the plane or up the plane. And then there's the vertical direction, which is up into the air or pushing down into the surface of the board or whatever's making the plane. Right? So gravity actually has then two components, right? It has the component pushing into the plane, and then it has the component making it want to slide down the plane. All right, and if you notice, I drew them in these specific colors because if this object is in equilibrium, then we could actually set these things equivalent to one another. So saying that this component of gravity must be equal to the normal force if the object's not accelerating up or down into the plane. And if the object is not accelerating down the hill, then the frictional force upward must be equal to the amount of gravity pulling it down. So in order to quantify these, I really need to know, well, what is this angle right here, so that I can use some trigonometry. I know this is a right angle, so I can use some trigonometry in order to figure out what the magnitude of those forces are if I were to know the weight of this, right? And it just takes some very simple geometry to reason out that this angle right here is actually angle theta, all right? So if I were just to extend this down and make it a right triangle, can you see how this angle here and this angle here and this angle here all add to 180 degrees, right? So these two would have to add to 90 in order to fulfill the triangle rules or whatever. So this angle must be the same as this angle, and this angle would be the same as this angle. Right? So hopefully you can see that. All right. So if I wanted to describe what my horizontal vectors are and what my vertical vectors are, I could say that all of the vectors in the horizontal direction, or all the forces in the horizontal direction, would be my force friction. And then this component of gravity, well, it's the opposite. So that would be Fg sine of theta. Whereas my vertical components would be Fn, or my normal force, and Fg cosine of theta, because this side here would be adjacent to the angle, right? Now, if they're in equilibrium, we can set them equal to each other, right, which might be the case. However, the object could be accelerating down the hill, and if that were the case, then I would just set up a sum of all forces equation saying that Fg sine of theta minus, because friction would be acting in the opposite direction, is equal to mass times acceleration, right? Now, it might get even, let me zoom out a little bit. It might get even more complicated in that we know that how to calculate friction. The equation for friction is equal to mu and then the normal force, right, times the normal force. And we have an equation for normal force here. So again, I could even further add in some other things for an accelerating situation where Fg sine of theta minus mu Fn is equal to ma. And then if I wanted to plug in for this my Fg cosine of theta, because I know they are equivalent, I could say Fg sine of theta minus mu Fg cosine of theta is equal to ma, right? So a lot of just plugging in and substituting in values. And then the last thing that I could do to sort of show you an example would be that we know that Fg is mg, right? So hopefully you see where I'm going here. Mg sine of theta minus mu mg cosine of theta is equal to ma. So in this example, you might notice that there is mass in every single term. And so you'll be given problems sometimes where you don't even know the mass of the block, but it's still, you are still able to solve for acceleration or the coefficient of friction or something relating to the problem. So don't let that stop you. All right. So this is just one example showing some substitutions. There may be other examples where we have a pulley over in this direction, there's more forces applied, or maybe even where there is a frictionless surface on the inclined plane. But hopefully now you will be able to recognize what sort of forces go into a problem when something is angled on a hill.